Okay, so good morning, and thanks for the opportunity for speaking here. My talk will deal with the conformal gauge theory. It's not 100% and not even 80% Bootstrap like, but there is some Bootstrap concept. And I listed here what are the objects we deal with. So I will deal with the endpoint correlation functions in gauge conformal field theory, but the computations that I will do more in concrete will be in n equal to 4 super Young Mills, which is supersymmetric and conformal theory in 4 dimensions, which I guess probably everybody knows already. And I will restrict myself to some special kinematical regime, which I will explain later, and it deals with some Null kinematics that is zero distances between the operators that participate in the correlation function. And in fact, as you know, when distances become small, there are divergences. One should then study a finite quantity and define and extract leading logs. This is what I will do. Leading logs for this correlator in special kinematics. And in fact, I have to point out that we believe, we know, and we believe also more in general that this result can be possibly relaxed, possibly generalized to at least first subleading logs. And the third, well, what I will present, in fact, is a non-perturbative conjecture that is a conjecture at all orders in the coupling of the theory. But it's purely conjectural, and it is checked up to order 5 in the coupling via some perturbative computation. It's perturbative computation. I don't know if I will be able to explain technically how to do, but the last part of the talk will be either with that, either will be absorbed by your questions. But I can already give you the handbook for it. This technique is called stampedes. And you can read about it in this paper. Again, by me and Pedro Vieira and me. So let me start with the first point. So concretely, the object I will deal with are indeed the correlators of this type. Where the operators will be single trace operators in this gauge conformal field theory. And therefore, when I say single trace, I refer to the trace under the indices of the gauge group, SU, N, and C means a number of colors. And these operators, since we are in CFT, they are characterized, of course, by a certain scaling dimension, which in general is correct perturbative the coupling with anomalous dimension, gamma. But we should choose these operators to be particularly simple, such that there is no any correction in them. So they are protected operators. And we can do this because of the supersymmetry of the theory. The theory has a supersymmetry which involves also the conformal group, and therefore you can build such operators that are so-called 100 PS operators who don't receive corrections in their scaling dimension. So finally, the operator O J in position at J is defined by a certain vector y of J as the trace of a certain power, say kappa, of yj contracted with phi, where phi are the scalar fields of the theory. There are 6 such scalar fields, so their dimension is 1. Okay. And the index I runs from 1 to 6. And the same index is for the vector yj, so yj is an index I, such that yj contracted with yj is equal to 0. So if I take this 6-dimensional vector to be null, this guarantees that this power of this scalar product is a rank k symmetric and traceless tensor, and therefore, by the symmetry of the theory, this operators are okay. So, in fact, I will start. So this is the type of object we compute, and we compute them in the planar limit. It's important to say that here the number of colors is set to infinity, such that the coupling the coupling of the theory G squared, what we call tooth coupling, is actually obtained from a double scaling of Young-Mills coupling going to 0 and the number of colors going to infinity, which makes all the correlators, or if you want, all the Feynman integrals that enter in the perturbative expansion of the correlator to lie on a sphere. Okay. This is quite important to say for the following. So if I start from 4 point, let me start for n equal small n 4. At 3 level, imagine a function of this type. At 3 level, that is when g squared is equal to 0, the only contribution you can have are simply product of scalar propagators, Bayer scalar propagators, that connect the point where the operators are inserted. And I'm gonna draw now the most general of such 3-level contribution. That's level at the points, clockwise, and therefore this is of course a planar that lies on the plane, as you can check. But I can also, for example, connect these 2 points, and I could connect 1 and 3. Or 2 and 4. So if I connect, for example, 1 and 3, I cannot connect 2 and 4 outside of the square. And you can see I cannot add any propagator without crossing another one. That is, without increasing the genus of the surface. Now, one such contribution, in general, is, of course, labeled by the number of Bayer propagators that connect the various points, and which correspond to the powers of their inverse distances, right? So, on propagator between the Bayer propagator between 1 and 2, stripped of its coefficient, is this kind of object, and the number of propagators between 1 and 2 will give me this kind of power. These objects are what we call skeleton diagrams, and we distinguish them indeed based on how many propagators are between each pair of points. And in fact, it is, we can consider each skeleton diagram separately and see how it gets corrected in the perturbative expansion. Simply thinking that the 4-point function will be equal to G 4-point function at the 3 level, made of the all possible skeletons, plus G squared times the one loop correction, and then higher corrections. And this one loop correction can be seen skeleton by skeleton. How? Simply because I1 of xi can be computed by the Lagrangian insertion method. That is, it will just be the integral over a 5th point of the 3 level of a 5-point function, which contains the 4 operators participating in the correlator and the interaction Lagrangian in the last point at 3 level. So one can play this game skeleton by skeleton, putting the interaction Lagrangian in the various points and correct. Now, this is what we deal with, in fact, the perturbative expansion of single skeleton diagrams. And now I can pass to point 2 and say what happens in the null limit, if you don't have questions.
I have a trivial question. So there cannot be all chiral, otherwise this is zero. So you are doing some of the operator will be anti-chiral, so that the correlator is vanishing, or am I missing something?
Sure. I mean, no, sorry. These are real scalar fields.
Real scalar?
Yes. There are 6 real scalar fields in the theory,
okay,
or if you prefer, 3 complex.
Okay.
Depends. So, in the null limit, as I was mentioning, the correlator diverges, and you all know very well from, for example, what happens in NLP, that logarithmic divergences are developed, for example, by a 4-point function. So if you consider a 4-point function and you take its OP in a certain channel, say 1, 2, 3, 4. Okay, let me say before. What is the specific null limit I want to take? Specific null limit I want to take for the endpoint situation is when the distances between consecutive points goes to 0. That means, for example, if you look at this skeleton diagram, that this perimeter have edges all oriented in a like cone direction. And then you can imagine for higher points a pentagonal like cone contour, hexagonal, and so on. Now, this limit creates divergences, as we know, when operators go at null distances, and one can see, for example, it's instructive to see what happens, for example, in NLP, where the distance 1, 2, and the distance 3, 4 goes to 0, and then also the distance is the distance 1, 4, and the distance 2, 3 goes to 0. Okay? So first of all, if well, as usual, I can introduce some conformal invariant variables, which are 2 in the case of a 4-point function, and consider the limit already in those variables. So well, you see that this limit of a null counter will be obtained sending, for example, it's not univoc, z bar to 0, okay, because 1, 2, and 3, 4 goes to 0, and successively z to infinity, okay? Because 1, 3, and 2, 4 goes. Sorry. Sorry, I have to relado. So, 1, 4 to 3. So if you write the OP, you will have, generally speaking, in the usual OP is sum over the exchange primaries. Then you have a term of this type, z bar to the twist of the exchange operator, which is in dimension minus the spin, times some product of hypergeometry, which is something like this to the S. I'm trying to be very schematic, of course. So here, this is a continuation of this line. So it's one term minus the one where the z bar is changed. So what matters is that I want to point out that, of course, when you take z bar to 0, this sum will be dominated by those terms that have a minimal twist. Okay, so by the shortest, lightest operators that can be exchanged in this channel. And of course, this limit produces logs already. Why? Because I can rewrite this quantity as log z bar, extracting the anomalous dimension log z bar g squared. You agree with this problem, or you need one more passage? Okay, you can raise the base to the exponent as logarithm, and then since we care only about so z bar is going to 0 and z for now it's finite, I am dropping. I'm just writing log z bar, and I'm also dropping the bare dimension because it's already fixed by selecting minimal twist, and I consider only the anomalous scaling dimension. So you see that the perturbative expansion of this object contains logarithm when z bar goes to 0, and in particular, the selection of leading logarithms I mentioned before happens because happens and simplifies a lot the problem for us. Because the expansion of gamma into powers, you can make an expansion of gamma into powers, first loop gamma 1, second loop gamma second, but then you see that when this logarithm explodes because the bar goes to 0, in order to pick the maximal logs, you have to define a double scaling that is send the coupling to 0 with the same speed, such that the product of g squared and z bar is finite. Otherwise, you would not get a finite quantity. And if you do so, you see that all the higher loop terms, since they have same power of log, but higher power of g will be cancelled. Okay? So, from the point of view of scaling dimension, we need to know only one loop scaling dimension. And then, of course, there is, once one takes this limit in z bar, with this leading log prescription, still there is a dependence left over in z from this second bracket, because when z bar will go to 0, the hypergeometry functions of z bar will simplify, but still there will be a dependence in z, and taking, you can believe, and probably you mostly know, that taking z to infinity, also this function develops logarithms. It's a function that is obtained summing over the spin at that point, so it's not just what you obtain from here, you should sum over spin. And for z going to infinity, you have additional logarithms, such that counting the logarithms that comes from here, so the leading logs from the anomalous dimension, and counting the logarithms that come from the second limit at order n in the coupling, you can have at most log z bar to power n, and at most log z to power n. Okay. So in fact, even if at the first step I define as finite quantity g squared log z bar in order to have something finite here, after every sum, and I take the second pair of edges to this null that is z to infinity, the extra logs make me really find a new double scaling limit, where now this is the finite quantity. Okay. Before it was just this first one. Now it will all be finite. And now we call this s squared. I hope I'm not missing in your, for you, crucial details in this discussion. I can tell you I'm not, but of course it's a bit quick to say. Just believe that this is the behavior, because otherwise I should explain you how, what is the limit of this function, how this constant simplifies. Believe me that the only important part in this expression when I take this double scaling, this double light cone limit, the dependency in g squared comes only from this factor, okay? And then the extra logs come from the resummation of what is left over where G square is set to 0.
So this is after your sum over string? Or?
This is after sum over string.
You assume this kind of logarithmic, standard logarithmic behavior as one with anomalous dimension?
No, so the anomalous dimension enters only here, right?
Yeah, as
so
the
I can
particular log of the spin, right? Has some constant.
Yes, that's true. But I'm not. I will resum over that quantities. Yes. I will. I'm really. We know in these theories, and it's actually that's why we say conformal gauge theory, because it's actually quite general behavior of one loop scaling dimensions.
So in front of this S square, you're going to find the cusp anomalous dimension.
Exactly. I mean, this gamma one is what you pointed out. This is one loop scaling dimension for the lightest operator. It's going to be that kind of object.
Yeah.
But then I still have to resum in S. And then find a function, which will be of some complication, and take the limit z to infinity and extract only the leading logs. That is something which is function of only S squared. And the nice simplification that happens is that if I consider the this type of skeleton diagram with its entire particle expansion, and I extract only the dependency in a square, that is this double scaling limit, it factorizes into two functions. It factorizes into two functions, which I'm drawing now, and can be associated to the internal part and the external part of the square. That is, you can visualize this object as being on a S2 sphere, and I'm cutting into two disks. Okay. And the two disks are indeed internal and external part. So if I have 1, 2, 3, and 4, then here I will have 2, 1, 3, and 4, identifying these edges, and so on. Okay. And here I'm missing a bridge which goes from 1 to 3, and so on. So let me call it, I just use this word bridge, those propagators in the three-level skeleton contribution that connects points that do not lie on the light cone, on the null counter. Okay? So this is what I would call bridge, and this is what I would call bridge. Okay? So the result, the nice property we know is that in this limit, as a function of S squared, this object is a product of two functions which depend only on the number of bridges in the corresponding skeleton diagram, and are very simple and calculated at all order. Sorry. At all orders in S squared. Okay? And this function I will call O of L1 S squared, O L2 S squared, and in fact their non-perturbative in S squared expression is exponential of minus x squared times the determinant of an L-tensile matrix whose elements are modified Bessel functions of the first kind, whose index is difference of I and j.
So, sorry, should one of the two have the connection between 2 and 4?
Exactly, the first one, sorry. Okay. So this is a very nice result if you want, which is because it is non-perturbative in this double scaling limit, and it has a further very nice property. That is, it solves a very non-trivial property. It solves a well-known equation, that is the total equation. So first, let me make another comment. before writing down the code equation. That these objects do not depend on the thickness of this square frame. That is, on how many propagators, can be 1 or can be 100, connect these 4 points in light cone directions. That is, this result is not valid only for heavy operators or light operators. Okay? It's quite general. And secondly, yes, I can write for you this equation that is the logarithm of OL over O0, satisfy a nice differential equation as a square this is after change of variable, it is nothing but the total one detailed equation for the function OL over O0, and in particular, so it's an equation where you can obtain tau L for any L if you know tau 0 and tau 1. Tau 0 is 1, tau 1 is this Bessel function. This is not our result though, but it gives us strong intuition how to go to general number of points, and now I can give a meaning to the name null polygons. Null polygons are these objects. So those objects, those polygonal objects that you obtain after the factorization of the planar endpoint function, defined by this double scaling limit based on null distances along the blue cone. So this result is in fact by Andrei Belitsky and Grigory Korchemsky, and you can find it in this paper. So at this point, I would like to show you the result, in fact. That is to tell you what, knowing all this, we can conjecture for any number of points in principle, but more concretely for 5-point and 6-point functions, which we believe is enough to know what happens for a general number of points. So I will pass from to the point 3 of my initial list. Let's start from n equals 5 points, and once again draw a skeleton at a tree level, where the 5 operators are connected, and in the most general situation, in order to respect planarity, I can connect, for example, 1 point with other 2, and that's all what can happen in the interior of the pentagon, and in the exterior I could do the same, choosing any other point, for example, this point. And I already know from here that it's important to label the number of what I call bridges. Okay? Say H and K, H prime and K prime. So the claim is that taking contour to be null, that is the distances xi, I plus 1 to 0, at the same time the tooth coupling to 0, such that g squared log xi, I plus 1 squared log I minus 1 square. It's finite, which is the analog of a square for more points. It is one variable. Now we have one variable for each vertex of the polygon. Well, this object factorizes, once again, in an interior times an exterior part at all orders in the variables ti square, that is at all orders in g square under the double scaling limit. And I will draw now only the interior because the exterior, as before, will be an object of the same type. This is H and this is K. And our conjecture is that this object is equal to E to the minus sum over K tk square, which reproduces the exponential in minus a square, times a function phk of the variables for the variables t1, t2, t5 till t5. Okay. And we know this function in principle non-perturbatively because we can look at what happens here and try to understand it as a solution of some more general code equation. If you observe this picture, you see that there are 2 points, 1 and 3, that play a little bit different role with respect to the others because they do not meet those yellow bridges. And in fact, to each point, we associate one-to-the equation, which let me use this notation, uppercase D to be the operator Tj, derivative in Tj. Therefore, you have two equations. So I'll move this definition upstairs. The first one, which deals with the point which is centered around point 1 and deals with the bundle of bridges of thickness h. And the second one, which does the same, centered in point 3, but for the bundle of bridges of thickness K. Okay, sorry. Okay. So in fact, you see that equations which is centered in 1 moves the index, only the index h in the function. And the equation centered in 3 moves only the index k in the function. In particular, if you look closer at this equation, due to the fact that the right-hand side is multiplied respectively by t1 squared and t3 squared, allows you to re-express, allows you basically to determine the solution of these equations just from the knowledge of the functions phk when t1 and T3 are equal to 0. Okay, from this boundary condition. This boundary condition will be enough simply because you are equating here the coefficient of a certain term, of a certain power in T1 and T3 by coefficients which deal with lower power, because they will be always erased by 1 T1 square or 1 T3 square. So you can always reduce your problem to the determination of this boundary condition. Let me be more precise on this point. Think that the function, the solution is at this form. This is the form of the solution. So it's clear that if you equate left and right hand side, for example, in this equation, the T1 square will make you will lead you to the left hand side. For example, you can have C and 1 and 5 HK, and in the right hand side you will never have the highest possible value of N1. So you can re-express it as a function of C N1 and 2 and 5 with values different H and K, okay, but where N1 is always smaller than N1. And this eventually leads you to express all these coefficients as a function of the coefficient when N1 will be 0, okay, which multiplies what is left over when T1 is set to 0. So, well, the missing ingredient is the boundary condition, but the boundary condition with some intuition and perturbative check can be seen to be some combination, some product of all the tau functions from the 4-point case. In particular, the logic is that you have to count how many bridges are emitted by a certain point, and add to the products tau functions with the that index, so index equal to the number of emitted bridges, and argument the cusp variable, the t variable associated to that point. Therefore, we have tau h plus k t2, tau h t5, and tau k t4 is nothing but p hk when t1 and t3 are equal to 0. This allows you to solve these functions p, h, k at every order in the variables t squared. And in fact, for this 5-point case, we can even express them non-perturbative in terms of determinants. Maybe, since the time is not much, I could discuss it in the end, but I prefer to complete the conjecture going to 6 points. Because 6 points is what really shows what should be the general setup.
Sorry, I'd just like to spend a bit more time, I guess. So TK, so you're looking at this 5-point node. TK is like the time associated with the cusp K roughly. And in your formula, you said T1, T5, because you're taking some ratio of 5 points over 4 points? Sorry, what is P? Can you just remind me what is P?
Yeah, T is the, sorry, is defined here. And I write it.
No, P.
Ah, sorry, P.
P, the thing on the left hand side. So.
Yes.
Right. It's like a very basic one. So the formula you have for P and K, why is it not symmetrical in all the 5 cusps?
It's not symmetrical in the T?
Yeah, you have T1, T5, and not the other T's.
Oh, there's.
No, sorry. Oh, yeah, sorry.
Ah.
And here as well.
M1 for a 500, sorry. And the C's you have.
I can do is that what recursively I can reduce all the C's to those C's where n1 and n3 are equal to 0, but those I know because I know the boundary conditions.
For 5 points, it's a function of two K's, basically. K1, K2, or not
Yes.
label them, but
Yes.
they're inside
Of H and K.
H and K.
Yes, and these H and K are shifted by respectively by two Todd equations.
Sorry, are you going to give some intuition as to why this is the correct guess with respect to the particular proper function?
Sure.
How do you guess?
The correct guess for the equations,
Yeah, why did you bring up this formula, these particular equations?
because, yes, so it's historical process, of course, and, well, we start from 4 points, and this is definitely more well-established result, in the sense that it has more checks. And here you see that there is that the number of bridges, so the solution with different number of bridges are related by the equations, but in fact, you know, in 4 points is the equation is simpler because due to conformal symmetry, these the variables that I would define in that way, T1, T2, T3, and T4 are essentially the same. Okay, so modulo sign. Not even in that way. So we started thinking how this could be generalized. And the first thing we checked perturbatively that when H and K are equal to 0, the exponential behavior is what we have. But this is quite solid because there are other papers that tell you, for example, about a bootstrap of 5.20 prime correlators or 6.20 prime operators. You look at their expression and you take this special double scaling limit and you recover it. Okay? And then we started doing what? Adding only one bridge. That is bridge only one direction. So kappa, k is equal to 0, and values of h. And wondering what is the analog of this equation where you have only one boundary bridge. Okay. So first we found the equations when only we have one bridge, and then we understood more and more. And similarly for this factorization, this was also guessed in the beginning. Simply, what does it mean to send T1 and T3 to 0? Well, it means that some of the edges who are going on the null cone, they will go slower, such that the corresponding variable is sublinear. And in fact, we could do perturbative computation in this simplified regime and start recognizing these tau functions that were already quite familiar for us.
Question? In the 4-point function, you took the limits asymmetrically. You took two sides first and then the other two afterwards.
It doesn't matter, but technically it's what we do. And it suited the explanation from the amplified point of view. So, yeah, let me pass to the 6-point function. I'll do it here. So the big news for 6 points, for which I will draw already only the polygon, okay? So the same factorization goes on in the same limit, is that not only bridge can connect next to neighboring points, but also points that are further away. And this is a situation that can, of course, generally happens when the polygon is as big as you want, so for any endpoints. So, And due to that, there is much more freedom in the way bridges can be inserted in the planar limit of this point. For example, I can have three bridges emitted all by the same point, which is something very similar to what was happening here. Okay. Or this equation, which is already some new configuration, some new topology, or the more symmetric one. So here we come at this point then to the conjecture, because you can see that here, in case of 5 points, there were 2 points close to bridges, but not being extremal of bridges. And so these 2 points, there were 2 associated Todd equations. So let's think in the same way. And here again, we have 2 points that is 2 Todd equations. Here also, only 1 and 4, so 2 Todds. And here 3. 2, 4, and 6. 3 Todds. But there is a crucial difference between these 2 situations, because you see, as in this explanation, the Toda centered in 1, okay? The Toda centered in 1 involves in the differential operators only the variables 2 and 5, apart from 1. And similarly, the Toda centered in 3 involved only 2 and 4, more than 3. This means that the Todd equation related to this point and this point are coupled in the point 2, as those 2 were. In the sense they both act on that value. Well, in this case, no, it is not the case. Therefore, the conjecture for these objects is e to the minus sum over k of pk squared, where the definition of pk is always the same. And then I have an object to determine the Todd equations depending on L1, L2, and L3 these variables, ti, which will be determined according to these 3 different system of equations according to the case. Okay, so if I write, for example, the case of the 3 Todas, there will be d2 plus d1 and d2 plus d3. Let me write only the differential operator. Or I have enough space. So I have one equation, which has 2 plus d1 and 2 plus d3. Okay, so it involves these 3 points. And it shifts on the right-hand side only the index L1. Here I'm not writing the index L2 and L3. They are there and they are the same. And similarly, you will have a second equation, d4 plus d3, and d4 plus d5 on log of h, which shifts L2. And similarly, there will be the third equation, so 6 plus d5, and d1 plus d6, log of h, which shifts L2. Having these shifts, once again, means that you can reduce the solution of this object to the case when, respectively, T2 T4 and T6 are sent to 0. But this object will be determined by the boundary condition for which you have an intuition and follow the same rule as before.
So in the middle case, in the third equation, L2 is never shifted. In the coupled case, L2 is never shifted.
L2 is shifted by the same
So
operation.
in the B case, which you have the two equations that you get, the two third equation, L2 is never shifted, if I'm not mistaken, just to be sure I understand. L2 in the B case that you have
In the
discussed.
B case.
In the B case.
Yes.
I'm just asking if L2 is not shifted.
There is no equation for L2. There is not an equation that shifts L2. And also in this first case.
Also,
Because,
exactly.
so in fact, if you look at this case, it's precisely the same as the pentagon case, but it differs only in the boundary condition because 2 emits also L2 bridges instead of 0, because it emits only the 2 bridges involved in TOTES. So here the boundary condition will be tau in variable T2 of variable T1 of L1 plus L3, tau of variable. So this is only for the screen, right? This line
No, that's
No, that's
is the
okay.
new boundary. It was not. It was here. Yes.
That's the one. Yeah.
This is the real one.
Yeah.
So this doesn't mean anything.
No.
This is, for example, a boundary condition according to the same law, counting how many bridges are emitted by those points that emit bridges, and take the product of tau functions accordingly. Now, I'm not going to write the equations for these two situations because, again, they are just two Todd equations, have the same form. What changes is only boundary conditions. Interestingly, because in this case the two equations are uncoupled, the solution will be factorized. So you will have a solution that depends on 2, 1, 6 from the first of the equations that move L1 times a solution that depends on 3, 4, 5 from the second of the equation. And that's it. Now, one can sit and think how to generalize these two endpoints, and it will be quite straightforward if you want. Now you have all the ingredients to consider the general polygon, because you have bridges that connect next to neighboring points, and bridges that connect further away points, and the associated set of todes and boundary equations. So, very little time is left over. I can try to answer your questions or to show schematically how we produce perturbative data against which we check this conjecture up to order 5 in the powers of t, that is up to order t1 square n1 t5 square n5 such that n1 plus n5 is equal to 5. Or, yes, either I can do that computation, but for the 4-point situation, which is simpler, or I can answer your questions.
Maybe quick question to make sure I understood properly. In the end, if you want the full correlator, you still have to sum over all topologies, and you have to multiply. The answers are factorized into these solutions, right?
Yes, so you have to sum always over skeleton diagrams. In general, some skeleton diagrams will be suppressed when you take the distances along the contour to be null, and only those ones who have a maximal power of these propagators along the contour will survive. But also those in general are not one single. There can be more in general. And you have, of course, then to sum over those which factorize, therefore to sum over products of polygons. But in fact, if you carefully choose the polarization vector, that are those y vectors that define the BPS operator, or more simply, more generally speaking, if you appropriately choose the operators that participate in the correlator, at least in theory with supersymmetry or some other internal symmetry, you can restrict in 4 points, 5 points, the correlator such that it has only one type of, it has only a very restricted set of skeleton diagrams that it's very simple to write in this way. It's pretty simple. I can provide this example, maybe rather to do the computation. Maybe it's boring. It's more boring, of course.
Sorry, also a question to be sure I understood. So using all these Todd equations plus this relation at 0, you are able to determine all the coefficients in the answers for H to all orders, arbitrarily to, I mean, up to, of course, numerically you stop at some point.
Yes.
There is no left over coefficient.
Yes, that's true. And in fact, more in the sense that for 5 points, these equations are associated to integrable systems. So for 5 points, we really have the non-perturbative expression for any number of h and k, so bridges, if we know the seed functions, that is the functions where h and k are from 0 to 1. So it's actually a nested determinant in a sense, the determinant of a matrix where each element is a determinant. And it generalizes in some sense the fact that tau was the determinant of Bessel function that I showed in the beginning. I would say that something similar should hold for 6 points and so on.
And this series have radius of convergence pi square. I mean, I remember the planar limit there should be given radius. I don't remember the paper maybe.
Here probably it's infinite radius of convergence, probably.
Because of BPS.
Not sure if because BPS.
So the Bessel
Like the Bessel, right? The Bessel is infinite radius, no?
Infinite radius.
I think so.
Yeah,
Just Bessel
because of the
function.
factor, yes.
A Bessel function, I think, if you Taylor expand, I think it's convergent, right? It's like expand.
Yeah, but this H, it's not clear to me.
But they, in the end of the day, morally speaking, they are generalizations of Bessel functions.
Yes. If you want to know what is the function, and that therefore I checked convergence of the perturbative data after guessing what is the, I cannot tell for H, but certainly for 4 points, because we just checked with perturbative data the equations were solved, but for the 5 points equation, or 4 points equation, yes, it is under control.
Is there any additional CFT that you can extract from here that you could not from proper function at the
I don't think so. Because we are in very special kinematics, and we are extracting only leading logs. I don't think this is possible. But what I can say is that for the 4-point case, even if you start introducing some sub-leading logs in the computation, still the Todd equation continues to work. And one could conjecture that that similar phenomenon happens for higher point, even though I cannot claim so. So this is at least how to get more information about the correlates. Okay, I think I'm over time.
I can take 10 more minutes if you want.
Okay, so I will explain how we produce this data. 4 points. So I'm providing a complete realization of those operators where x, z, x bar, z bar are now complex scalar fields. So you remember we had 6 real scalar fields. You can make combination of them of the type phi I plus I phi j, okay, in order to get scalar fields x, z, and y, x bar, z bar, and y bar. Here I deal only with the first. And if I start drawing the skeleton trilateral graphs for this particular choice, so this is in point 1. I will always have this equation. Let me use more fields. Okay, so in point 1, there are 2 fields x emitted. In point 3, there are 2 fields z absorbed. And in point 2 and 4, there are both emitted and absorbed fields. And these operators, I can guarantee they respect the definition of protect one-half decay operator I gave in the beginning. So the generic skeleton diagram that you can obtain has a certain number of bridges internally and externally, n and n, such that their sum is equal to n, fixed by the correlator. So let me choose a conformal frame, sending point 1 to be sending the 4 points on the plane, which is always possible just by means of conformal transformation, such that the first point is in z bar, the second point is in 0, the third point is in w bar, and the last point is at infinity. So now we have to take the limit on this object. That is setting z bar to 0 and z to infinity, and extract the derivatives. There are a few steps to reach that result, but in fact the procedure is pretty schematic and simple. Because first of all, you can, well, we just send indeed the z bar to 0, making this edge to be null. Okay? If you are familiar with light coordinates, I'm using light coordinates. Okay? So if I send z bar to 0, this edge becomes null. Similarly, here I inserted also w bar for convenience, and so I want also, I have also to send w bar to infinity in order to make this second edge to be null. And I can expand now these 2 null edges along the light direction. That is, expand the operator that sits here around the point 0, and then expand the operator that sits here around the point infinity. How to expand? Not with the usual OPE or light con OPE, which would require me to know what are the exchange operators, and therefore to diagonalize the dilation operator, to know what are primaries exactly. No, I will just do a Taylor expansion. Okay. So the first edge will just become a sum in J of light conderivative power J or J factorial of trace x squared times the operator that sits in 0. That is yeah, so x bar y to the m z y to the n. Let me point out that I'm choosing already that specific permutation inside the trace that corresponds to this drawing. Okay, so I have one x, and then I have m y's, one z, and one n. And all this is in 0. Times the distance along the line, z to the j. It's a Taylor expansion. So in fact, more compactly, I can write sum in j of z to the j top state of spin j. And similarly downstairs, expanding around infinity, I will have some other j, now trace of x bar, y bar n, z, y bar n, derivative j times of trace z bar squared, all in infinity, 1 over w to the j, because I expand around infinity. And this I can call so w to the minus j times bottom state as a bracket. Okay? That's the
Sorry,
So-
in this equation there's a, in the first equation there's a big z in the trace and a small z to the j, right? Is that to the
that's yeah, thank you. I reduce it. So, well, those two sides can be strongly simplified according to 4 considerations, 3 or 4 considerations. Well, first of all, now we are looking, we are taking this distance to be null, so basically we are looking at the operator that flow in the light cone P in this direction. So it's clear that what can flow in this direction? Well, what matters are the shortest operators, the operators of smallest possible twist, and are obtained contracting all the possible number of fields between these 2 points, and similarly between these 2 points. Why? Because this will be, of course, will lead, of course, to leading contribution, because when the distance goes to 0, it will be enhanced. Therefore, I can already cancel the couple x bar that is connected here, and the downstairs similarly for z and z bar. First point. The second point is that I can regard at this point the operator as this single trace leading twist operator that is exchanged, as usually in OP. Okay. And so having simply one trace. At this point, I can identify, as usually happens in n equals to 4, but why not? More in general, even symmetry. I can identify a single trace operator, its various fields, as sides of a spin chain. For example, trace of x, y to the m, z, y to the n. I can rewrite it simply. Simply as a x, y, z, bunch of y, where here I have n of them, and here I have n of them. And the insertion of a derivative, for example, on the first side, is a kind of SL2 excitation, like from derivative acting on the first. Okay, now we come to what comes more from the specific limit, the strongest simplification. The strong simplification is, you see this trace, but we know that after the second limit is taken, okay, which means z to infinity and w to 0, there is a factorization to 2 squares. So in fact, we care only about those fields that are internal or external, but not both at the same time. Let's concentrate on the interior. So I see flowing x, y, n fields of type y and 1 field of type z, right? So this operator will be actually z, better, yes, x, y to the n, sorry, I miss, okay. X, y to the n, and z, y to the n, and x. Okay. And secondly, since we are interested on the leading logarithm in the special kinematics, in fact, we will see that the quantum correction do not care about the the differences in internal symmetry of the scalar fields. But everything comes only from the part of the dilation operator which is related to kinematics, that is to excitations due to light conderivatives. What I mean is that I can just write this instead as trace of z, z to the n, 0. I don't have to distinguish different fields. And finally, well, I should probably have been done already in this passage. Due to this factorization, the trace is not closed. That is, in spin-chain language, this state does not have periodic boundary condition, but it's open, an open spin-chain state. So finally, the top state can be rewritten as djz times z several times, which is n plus 1. Okay? And similarly, the bottom state is z to the n plus 1 derivative in j of z. This state is in point 0, this state is in point infinity. Okay. So finally, we are ready to produce a lot of perturbative data because we have just to compute quantum correction, right? That is, after sending z bar to 0 and w bar to infinity, we are left with a function of z and w, which I simplify according to these transcriptions, which are checked. Okay, so the computation has been done in the more rigorous way, and then check that it simplifies with this consideration, for which is much faster and much more efficient to produce data, and that's why then we stick to it. Okay, so this quantity is given by the sum in j and j prime of z over w, so z to the j w over j prime, this guy, bottom of j prime, evolution operator, which is e to the g squared log z bar over w bar, a certain Hamiltonian, I will explain, top and j. What do I mean? Well, this is what you have in AOP, right? I send the two edges, 1, 2, and 3, 4 to 0. So what you would have in AOP u that goes to 0 with power delta over 2. But for what?
Just again presentation. This is z bar and w bar into z and u. So the
Yes.
expressions there were like z bar to the j and w bar to the j, and here, like in the sum, do you have z to the j divided by w to the j prime, or there is bars?
This is z and w. This is z and w. So I send z bar to 0 and w bar to infinity, such that the orientation of these two edges is on the light cone. At this point, I can expand the two edges along the light cone. That is injecting light cone derivatives. And in this way, I'm creating the states top and bottom.
Okay.
These states undergo a certain list of heavy simplifications for what we want to compute. Okay. So at this point, I really take the bra from the expansion and the cap after simplification, and I consider the quantum correction. That is the evolution, which is given by u to the delta over 2. I already explained in the beginning that what matters for me is the leading log. So I have the log of the parts which is exploding times g squared. Time and operator h, which is the Hamiltonian of the system, is nothing more by the one loop dilation operator that can be spelled as a spin chain nearest neighbor Hamiltonian. This is starts to be apparently technically complicated, but it's not, because it's a very, very simple operator whose only action is to move derivatives from one side to the other of the spin chain, and in order to move these derivatives, you have to pay a certain price in energy. So finally, you can really, with Mathematica, compute this type of object up to very high order in the expansion in g squared times the log, and in fact guess the summation in j and j prime. Well, since this is SL2 invariant, I can already say that j and j prime should be the same. So you really have the sum over one variable of the result that you can consider loop by loop, and this is what produces the perturbative data, which we call stampedes, because indeed, if you have a state, the derivative is only on the first side, and it is in zero, which should be bracketed with a state where derivatives are only on the last side and it is in infinity. Of course, what the Hamiltonian should do is move all the derivatives from the first side to the last side, such that the states are not orthogonal. And in some sense, this is a picture of a stampede of animals or in a certain direction. That's the inspiration there. Okay, so if you have any questions.
I have one question. Does it matter how you approach this null limit? Like, do you start from all space-like separated points, or can you?
Indeed, first perturbative data are produced in a certain order. First, I indeed take two edges, for example, in the square or in the pentagon, two edges to be null. I do this expansion, and then I obtain a function which is still finite in Z and W.
So to take them to be null, does it matter if you approach null from space-like or from time-like separation?
No. No. I don't. You just have functions and take the limit of the ratios going to the point it should. So I don't think we distinguish.
Further questions?
Sorry, this is because chiral ring natural 1.5 BPS that they commute also for time-like configuration, or what? I believe.
Well, I am not sure about this point, but yeah, what I want to say is just that in all the computations, all these perturbative computations, I never have to define the domain that where Z and W lie when I approach this limit. So there can be some subtleties I'm missing, but extracting the leading logs seems totally fine.
Well, it does look multi-value. If I were just to take Z bar around the branch, one branch point, there are logs. So somewhere, maybe you are assuming that the only the first branch might correspond to a specific approach.
And this, yeah, but if you go, you may be right, but if you go around the branch cut, you usually get Poisson monodromy, which is a constant.
So it's a bleeding.
I would say it's a bleeding.
Let's send this figure.